Hello, Internet! Last time we had a look at the data processing pipeline of the original Word2Vec in TensorFlow, TensorFlow 2.7. And as you can see here on the screen on the left side, we have here the official TensorFlow tutorial on Word2Vec. And today we are gonna have a detailed look on that. Let's just give me a second. Come on. Here. Preparing some training data for Word2Vec. So now we are gonna activate everything we learned in the last video. And now we create here on the right-hand side, we have our Jupyter notebook, we have TensorFlow loaded, and now we create a TensorFlow data pipeline for text preprocessing. And now we combine two things. We combine all the functionality that TensorFlow gives us in its specific data pipeline, and we're gonna make use of something beautiful, and this is pre-processing layers in Keras. So we combine those two, and as you can see, it has been updated last third of 2021. And if you are not familiar with pre-processing Keras layers, it is quite easy. The Keras Preprocessing Layers API allows developers to build Keras native input processing pipelines. So it is to optimize the input processing while running the model to have some parallelization going on within TensorFlow. Can be an independent preprocessing code or whatsoever. You can export your models and of course. And now the available preprocessing in Keras layers. Here we have our use case, and this is text preprocessing. And if you remember, in the last video I showed you about TensorFlow Keras layers TextVectorization, which turns raw strings of our text, our sentences, into an encoded representation that can be read by an embedding layer. And this is exactly what we will use today to show you how it works. And to understand how we can prepare this layer, we have to know one other thing, that some preprocessing layers have an internal state that can be computed based on a sample of the training data. And the list of stateful preprocessing layers is, surprise, surprise, our text vectorization layer. And this holds a mapping between the string tokens and the integer indices, like I showed you last video. And crucial is that these layers, our text vectorization layer, are non-trainable. Of course, you want to have your vocabulary more or less stable. Their state is not set during training. It must be set before the training to define your vocabulary, either by initializing them for a pre-computed constant or by adapting them on your data. And this is exactly what we're going to do. We're going to adapt the pre-processing layer on our data. And you set the state of a pre-processing layer by exposing it, of course, to the training data. And this is done via the adapt methodology. And I will show you this. Just to note that the adapt method needs either a NumPy array or a tf.data.Dataset object. So what we're going to do, we're going to create a tf.data.Dataset object and apply the Keras pre-processing and the adapt method to get our vocabulary. And just before we do this, notice the pre-processing data before the model or inside the model. These are two options you have. And what we are going to do, we choose option 2. So we apply to our TF.data.Dataset, remember we already have it, as to obtain a dataset that yields batches of pre-processed data. And this is the easy notation we're going to use. With this option, your pre-processing will happen on your CPU. So we know that our Colab notebook for this pre-processing, CPU is perfectly fine. It will go asynchronously and will be buffered before going into the model. And if you have now the prefetch, which is another video I showed you on the particularities and advantages of TF data, and you have a TF data auto-tune enabled on your dataset, The pre-processing will happen efficiently in parallel with the training of your model. And this is what you want. You want to have a fast calculation, a pre-processing in parallel with the training of your model. So we're going to use this prefetch TF data auto-tune mechanism. And as is stated here, this is the best option for text vectorization and all structured data pre-processing labels. It's also to be a good option if you're training on a CPU. If you're training on a TPU, just for the advanced users, you should always place pre-processing layer in the data pipeline of TensorFlow. So this was it for the theory, and now we go back to encode this. Now first, as I told you, we have now to create our TF dataset. And the first line, as you can see here, is we have our text line dataset because my data is in a text file. So what we're going to do, we create the TF dataset. And then we just have a look how many lines we just loaded. And if you want to have a look at the element specification, you have a simple .element specifier where you can have a look at it in this. And if you just want to have a short look for the first 10 lines, let's say, how does our dataset look like? We have this simple command where we say for line in text in the dataset, take the first 10 and line.numpy. This will take some time because I suppose we have about 100,000 sentences, and I have taken them all from some scientific literature on some European research projects. And as you can see here, we have 129,000 sentences. And to give you a feeling about the sentences, this is the kind of sentence we will encounter. I loaded with my dataset. So you have no normal English language, some small talk. No, this is about a scientific language. So we will build our very specific vocabulary with only the vocabulary we need for this scientific literature. And here we go. The first thing, of course, is to define the batch size, and just for convenience. And we can do it in this Colab notebook where we have close to 13 GB of RAM available. I set my batch size to 32K. You are free to choose your size, whatever you like. And my vocabulary size, I saw it 30,000. Vocabulary items, if I have 130,000 sentences, not so bad. I think if you calculate the vocabulary size without any limitations, I think for my dataset it is close to 50,000 vocabulary items. Now the next parameter we have to set is the sequence length. And the sequence length is the maximum sequence length that will cause the layer to pad or truncate sequences, this means sentences, to exactly the sequence length values. So we have about a sentence length of 20 words. You can use text vectorization pre-processing layer to vectorize sentences from your text corpuses. Yes, this is, yeah. And for the first few sentences, the text needs to be in one case, so in lowercase, and the punctuation needs to be removed. To do this, we define a custom standardization function that can be used in our text vectorization Keras pre-processing layer. So let's do this. We have here our function custom standardization. The first thing we do is we have here a lowercase, and then we just say, hey, get rid of all our punctuation. And now we can use this here within our text vectorization Keras pre-processing layers. The maximum token size is, of course, our vocabulary size. We want to have integer as an output in the output mode. We want to have the output sequence length to be equal to the sequence length. Be careful, this is only valid in integer mode. And you can also have n-grams included, but for the moment, we just leave n-grams out. We are just going for simple words. And of course, the whole game is to build Keras native input processing pipelines. to be as fast as possible with all the functionalities we have with Keras in TensorFlow. And as I told you, next, oh yeah, we have to run this. Sorry, define the function. And then the next step is simple to, as I showed you, run the adapt command on this. It fits the state of the preprocessing layer to the data being passed before the model. And of course, if we want to get your vocabulary, we just say vectorize layer dot get your vocabulary. And here we go. If you want to have a look at the first 20 terms ranked for frequency, you see that since it's a scientific literature, we have here technology, data, European energy system, innovation, knowledge, design. So not the typical standard English conversational words, but this is about a little bit about a scientific conversation. And then, as I told you, with the prefetch auto-tune, we are gonna apply this now to really do all the optimization we can do for the parallelization of the Keras layer, preprocessing layer, in parallel with the model calculations. Of course, we have then to flatten this into a list of sentence vector sequences or sentences. Just do this, and if you want to have a look how we end up with our optimized input data structure, this will give us now, oh yeah, this again is reading our 129k sentences, so this is going to take some time, 10 seconds, 15 seconds, come on. And then you will see how the numerical index encoding of our sentence happened. And here you have our sentence, and it says multidisciplinary, multi-actor consortium of academics, something develop. And the numerical encoding you have here, this is our numerical index encoding of our words. So we have our vocabulary, we have defined our Keras pre-processing layer. And if you're unfamiliar with this, go back to my video on TF data. I'll leave a link for you right here on the right top corner. And now we're going to do, and now we just generate our training data. And if you are familiar with this function, this is a function we defined last video, where we ended the video with this defined training data, where we have our Keras preprocessing, the sampling table. Then we have our skipgram, because we're using the skipgram model here, where we define our skipgrams. And then you remember there was this topic with the TF random log uniform candidate sampler, where I showed you that I think there are some inconsistencies, but again, maybe I'm wrong. If you find out about it, please leave a remark in the description of this video. And then we just build it, and what we end up with are targets, words, context words, and the labels. And remember, if we have for a pair of target and context words that are actually standing right next to each other within a window, we have the label 1 for true. And if you have some negative sampling, this means you have a target word and a context word in this pair that is not within the window size that we define, then the label will be assigned 0, and we just reduce the whole softmax logarithmic probability distribution of Word2Vec from the original complexity down to a classification problem between 0 and 1. And this is the beauty where we have here Word2Vec in our TensorFlow code. So now let's go back. This is going to take now some data, because now we're going to run this function. We have a window size of 7. So this is quite large. So from one target word, we go 7 words to the left and 7 words to the right of this target word. And we say we create word pairs, and those word pairs get the label 1 for true. And we create, of course, 3 times more negative sample values, word pairs, that have the label value of 0, and those are wrong combinations to enable our Word2Vec model to learn the right combination of words so that the vicinity of semantically closely related words, those vicinity becomes closer and closer together as we train our model. So let's start with the training. And as you can see, this is gonna take just 10 minutes or less than 10 minutes, which is really fast for the amount of word per generation we're doing. And let's have a look at RAM. We have currently 1.7 gigabyte of RAM, and I will be back in a second for you when we finish this calculation. And after 11 minutes and 1 second, we are back with the calculation. We have done all of our 129,071 sentences, and we have finally our data that we need, our target words, our context words, in a word pair with a specific label, either 0 for true or 0 for false, which constitutes our negative sample set. As I showed you here, when we look at the system RAM for this particular configuration, you will see that the system RAM here peaked into the yellow. This means above 10 gigabyte of RAM. And if you increase your vocabulary size, as I showed you here, to 50K, and you have about 300,000 sentences, you will crash your memory immediately. Even if you reduce the window size to 5, with 50K of vocabulary size and 300K sentences, you need about 50 gigabytes of system RAM to do the calculation. But this was just a remark on the performance. And oh great, this is nice. And we are back for the training. So now that we have our training data, we can configure the dataset for performance. Now we do the fine-tuning again, because to perform efficient batching for our Word2Vec model, we use again our tf.data.Dataset API. And what we have is we have elements of a word pair, where the word pair is the target word, and a single context word with a label. You remember, 1 or 0 for true or false. And we define a simple buffer size. And then we do a tf.data.Dataset from our tensor slices. And we have the targets, the concepts, and the label now calculated. The data is ready. And we do the shuffle. Yeah, we do the shuffle rubble. Of course, we batch it. And then we have a look at the dataset. Let's perform this calculation. And of course, as you remember, we cache it in memory. And we do the prefetch with the auto-tune to further increase our performance, to have a parallel execution of the pre-processing with the training of our model. And this is done, and now we have our prefetched data set with specific shapes. And this is great. And what we are now in is finally our Word2Vec model. And again, here we use in 2022 all the goodies that we have in TensorFlow and Keras, all the latest development. And what we do is we use some Keras Subclassing API. And if you want to have a look at this, there's a beautiful, yes, thank you. Yes, I know, you're Google. There's a beautiful description about layers and models via subclassing. And as you can see, you have here an init command, and then you have your specific call function. But not to make it any more complicated, let's stay with our example. What we have, if you want, 4 layers. At first, of course, we have the target embedding. And we have here a TensorFlow Keras layer, and this is an embedding layer. And the job he does is very simple. It just looks up the embedding of a word. So let's say sunshine, and this is the numerical embedding, integer embedding of, I don't know, 212. And this is all it does. And the number of the parameters in this layer are, of course, you have your vocabulary size and your embedding dimension. Now, we will use as an embedding dimension 128, but you can go with 256 or 512 or 1024, whatever compute resources you have access to. And then when we have the target embedding, of course, you need a context embedding. And this is absolutely the same, except we are doing now not for the target word, but we are doing it now for the context word. So perfect, you have two embedding layers, and if you want to find if the target embedding and the context embedding are indeed true, what you can do is you perform an inner product, or a dot product as they call it, and there's a beautiful function, a layer. The layer is called Keras layers dot, the dot layer, and what it does, you will not believe it, it computes the dot product of a target and context embedding from our training pair. And then you just flatten. The fourth layer is that you just, flatten the Keras layers into logits. And with the subclassed model, you can define the call function that accepts our pairs, which can then be passed into the corresponding layer. And the dot product, yeah, this is clear. If you assign a layer instance as an attribute of another layer, the outer layer will start tracking the weights created by the inner layer. Yes, this is exactly what we want. We recommend creating such sublayers with the init method. And this is, as you can see here, this is what we use. We have here our init method, and we create here our target embedding layer embedding, where we have, of course, our vocabulary size, our embedding dimension. The input length is 1. It's one word we have as a target word. And then we have, you will not believe it, the context embedding, where, of course, the input length, we have the one that is true and the number of negative samples to it. This is all there is to the init method, and then leave it to the first call to trigger building up their weights in the layers. And this is exactly what we're going to do. We define here our call, where we say, okay, we have our word embedding, then we have our context embedding, and what we want to do is we want to calculate the inner product, or the dot product, between the word embedding and the context embedding, to get a measure of similarity, of closeness, if you want, in a vector space. And they don't just use a single dot product, but what they use here is, again, a TensorFlow function, and it's called gensim. And this tensor contraction over specified indexes is an outer product. And this allows defining tensors by defining the element-wise computation. And if you think, heaven's sake, what is BE to comma BCE to BC? This is a specific notation you get familiar with, and then you can use gensim. So the dot product, we will get a return. We will get return the dot product of our two embedding layers. And this is it. This is our whole Word2Vec model, with the beauty in a methodology called Keras Subclassing API. And here we go. Everything you need is the embedding dimension. As I told you, we make it simple, 128. Then the number of negative sampling. Again, we always chosen 3, so we stick with 3. Then you have your optimizer, and I just use the classical Adam optimizer. You can use an Adam or whatever. We have a cross entropy for the loss. And of course, our matrix, very simply, I stay with accuracy. And then if you want, but this is an additional bonus point if you want, you can have an exponential decay function for the learning rate. You know, if you keep the learning rate constant, maybe you are not you will not achieve the best training of your model. So I have here learning rate schedule, where I have a learning rate defined by this exponential decay function. But you can choose also a linear or a constant learning rate. This is just some fine-tuning we will do. Yeah, this is just what I always do. I have some checkpoint and I have some early stop, but we do not have here some validation or test and training data set, because we want to have the embedding and the results for each and every word. And then with this fine tuning, and you can see here, I have my callbacks with my checkpoint, with my early stopping, and with my learning rate scheduler. And now let's say my number of epochs, or let's do 20 at least. I mean, otherwise it's not really a thing. And our data set here, our optimized data set, now it comes into play, and now we start training the model. And great, I forgot to activate everything here. I stopped here, so we have to define the model. Jesus. Sometimes, Jesus. Then we have to define our compile function. Then we have to define our exponential decay. We have to define our early stopping. And then now, finally, we are able to run our model, train our model. Then sick. So as you can see, it takes about half a minute for one epoch. And we have 20 epochs, so this makes about... I will be back in a second. And we are back. And as you can see, it does not take so long because look, our 20 epochs started. The first one was 32 seconds, but then it accelerated to 15 seconds per epoch. And this is amazing. Imagine we have 130 kilo of sentences. We have a vocabulary size of 32 kilo. And this is not bad at all, 15 seconds per epoch. And we achieved an accuracy of 92.4%. And if you have here a look at the learning rate, you can see since we have an exponential decay of our learning rate, especially optimized for 20 epochs, but you can insert in this formula that I showed you whatever value you like, you prefer. You can say that the learning rate is really going down to 0.001, and we started with a learning rate of 0.01. So we have here really a learning rate that is adaptable, that becomes finer and finer. And after 20 epochs to have an accuracy of 92%, this is nice. And of course, if you want to have a look at some visualization, you see here that the model accuracy shows our typical accuracy learning rate. The model loss is what we expect it to be, but the final test, if this converging really happened on some point which makes sense and not about some no-nonsense point in our vector space, we will have to have a look at it in the last and third part on this video mini-series on Word2Vec. So, for the validation of this trained Word2Vec model, I see you in the next video.